from reward hacking in rubric-based reinforcement learning to meta-RL for deep research agents, and the limits of self-verification in medical vision language models. Today's papers reveal both the promise and the pitfalls of using rubrics, judges, and reflection to guide AI systems. We'll explore how models can gain weak signals, how rubric-driven decomposition can boost long-form reasoning, and why self-checking often fails when the stakes are highest. Stay tuned for a deeper look into where AI evaluation works and where it breaks down. Let's explore the first paper, Reward Hacking in Rubric-Based Reinforcement Learning. This paper studies reward hacking in rubric-based reinforcement learning by separating two failure sources, verifier error and rubric misspecification. Using Qwen 257B, instruct trained with GRPO on 12,519 medical and 19,806 science prompts from Rubric Hub. The authors compare a weak training verifier, GPT Stereo Mini, against a stronger GPT OSS 120B verifier and evaluate both with a three-model reference panel composed of GPT-5, 4, Gemini 3 Pro, and Claude Opus 4.6. Under the weak verifier, proxy reward rises sharply, while reference reward plateaus, and the fraction of newly credited criteria later rejected by the panel climbs from 39% to 65% in medical and from 63% to 75% in science. HealthBench reproduces the divergence, with the weak run peaking at step 200 and then losing 25% of its gain by step 450. The paper identifies three recurring verifier failure modes: partial compound criteria, implicit as explicit inference, and imprecise verification, and shows they are stable across domains and model scales. It also introduces the self-internalization gap, a verifier-free signal based on the policy's log probabilities, which correlates with reference reward at R equals 0.91 to 0.97 and peaks within 100 training steps of the consensus optimum. Even with strong verification, rubric optimization can still degrade quality. Rubric-based judges prefer the RL checkpoint on 85.8% of medical prompts, while rubric-free judges prefer the base model on 78.4% because the rubrics overweight presence-based criteria, which account for 90.2% of weight, and underweight absence-based failure modes. Let's explore the second paper, Rubric EM Meta-RL with Rubric-Guided Policy Decomposition Beyond Verifiable Rewards. Rubric EM introduces a rubric-guided Meta-RL recipe for deep research agents that operate beyond verifiable rewards, where outputs are long-form reports rather than exact answers. The core novelty is to treat rubrics as a shared interface across planning, judging, and memory. The Qwen 3 8B agent first generates self-rubrics in a 4-stage scaffold: plan, research, review, answer, then trains with stage-structured GRPO, which assigns causal stage-wise credit from rubric scores instead of broadcasting only a terminal reward. A shared backbone reflection meta-policy is trained in parallel to distill judged trajectories into reusable natural language guidance stored in an agent rubric bank, enabling both within-episode refinement and cross-episode transfer. The system uses Gemini 3 1 Pro for SFT data generation, Gemini Flash as the rubric judge, Google Search grounding plus Semantic Scholar snippet search, and an asynchronous one-step delayed reflection pipeline to avoid extra wall clock bottlenecks. On 4 long-form benchmarks, HealthBench, Research QA, Deep Research Bench, and Research Rubrics Rubric EM, 8B reaches a 55.5 average score after 1,400 RL steps, improving from 49.2 at SFT and outperforming DR Tulu 8BRL at 53.6, while approaching proprietary systems such as OpenAI Deep Research and Gemini Deep Research. The paper also reports strong out-of-distribution short-form transfer, with Rubric EM, 8B, RL reaching 73.5 average on Simple QA, 2Wiki Multi-Hop QA, WebWalker, and Deep Search QA. Let's explore the third paper, Verification Mirage Mapping, the reliability boundary of self-verification in medical VQA. Verification Mirage argues that self-verification is not a dependable safety layer for medical vision language models in visual question answering. The authors introduce VeriMap, a diagnostic framework that separates verifier behavior into discrimination capability and agreement bias, then evaluate 6 open-weight VLMs, Qwen 2, 5VL, 7B, Instruct, Gemma, 3, Phi, 4, Multimodal, Instruct, MedGemma, Huatuo GPT Vision, and Lingshu across 5 datasets: VQA RAD, Slake, Path VQA, PMC VQA, and MedExpert QA. Across 42 task model cells spanning 7 task types, the dominant regime is the verification Mirage, where verifier error is high and false acceptance is high simultaneously. On the logistic mixed effects analysis, a generator error increases verifier error odds by 57.4 times, p is less than 0.001, with coupling varying sharply by model and task. The key novelty is that this failure is task conditioned. Differential diagnosis, causal explanation, and disease classification sit deepest in the Mirage, while quantitative measurement is most resistant. Saliency analysis shows a lazy verifier effect, with verifiers attending less to image evidence than generators, and cross-verification partially helps, reducing false positive rate by roughly 12-20 percentage points and verifier error by 2-5 points, but not eliminating the problem. In multi-turn actor verifier loops, 69.5%, 87.1% of initially wrong answers are locked in by false verification after 4 revisions, showing that reuse amplifies rather than corrects error. The paper's central claim is precise. In medical VQA, self-verification often reproduces model confidence rather than independently detecting mistakes. That's a wrap on today's AI paper highlights. Thanks for watching.